The last topic in chapter 6 is periodic properties. Periodic properties are properties of the elements, and we're going to look at them as we go across the periodic table and see if we can come up with some sort of predictions. What's going to happen to the size as we go across, or what's going to happen to the energy it requires to pull off an electron as we go down. So periodic properties. So the first one we need to remember are valence electrons. And valence electrons are going to be the ones with the largest quantum number. They're going to be on the outside and they're going to be reactive. And the valence electrons are going to give ourselves the first periodic property, which is how these guys react, in that we know that our metals are going to lose valence electrons. We know our nonmetals are going to gain, and they're going to gain until they get some point of stability. For the nonmetals, this is almost always going to be the nearest noble gas. For the metals, if they're in the representative, it's going to be the nearest noble gas. If they're the transition metals, they're going to go to some point of stability. So we're going to start out here with our atomic radius. Now, our atomic radius, if we take a look, it gets fairly obvious as we go down a group. And as we go down a group, we're going to go, let's do group 1, and we're going to go from 1s, 1s1 to 2s1 to 3s1. And we know that as our quantum number increases, we're going to have further distance from the nucleus and our radius is going to go up. So the first thing we're going to do is just sort of imagine that our elements are going to do this. Now, what happens if instead of going down, we go across a row? So if we go across a row, and particularly we look here at sodium, and we look over here at chlorine, what we're going to discover is that, in fact, it is going to decrease in size. So if we go across a row, it in general is going to decrease in size. Question here 1 is why? So first of all, we're going to answer that one. It decreases in size because if we compare sodium to chlorine, sodium here has 11 protons, chlorine has 17 protons. The electron configuration for sodium is neon, 3s1, and the electron configuration for chlorine is neon, 3s2, 3e5. Now, first of all, these are both in the n equals 3. Because these are in the n equals 3, chlorine and sodium should in fact have pretty much the same size. But what determines it, instead of being just the quantum number of our valence electrons, what also affects this is the number of protons. And the key here is that in chlorine, we have 17 protons pulling on electrons in the n equals 3. And in sodium, we have 11 protons pulling on electrons in the n equals 3. This is a greater pull. And when we have a greater pull, it's going to pull the electrons in tighter. And as we go across a period, we find our radius is going to decrease. So the best way to do this, and this is stupid, so I apologize, is to imagine you have a snowman, and your snowman is going to fall over. And when your snowman falls over, he's going to fall over to the right, and he's going to get smaller. So it's going to get larger as you go down. It's going to get smaller as you go from left to right. You can look at the details as to why this occurs when you look at Z effective. Z effective is part of it. The also is how far the electrons penetrate in terms of their orbitals, the details of which I'll leave for a good quantum mechanics class. So, radius. If we take a look at our radius here, if we go from helium to lithium, is going to go up. Lithium is going to be the largest element that is in our period 2, and then it's going to decrease. Sodium is going to be our largest element in period 3, and then it's going to decrease. Potassium is going to be the largest element in period 4, and we're going to kind of ignore the transition elements. But again, we know that as we go down a group, it's going to get bigger. So potassium is bigger than sodium, which is bigger than lithium. And as we go across a group, it's going to do what it does right here. It's going to get smaller. Now, this is also going to affect the radius. And when we look at this, it's going to be kind of consistently what the number of protons are versus number of electrons and what orbitals these our electrons are in. So aluminum, for example. Aluminum we know is neon 3s2 3p1. If we lose 3 electrons, we're losing the electrons in this outside n equals 3. Therefore, we only have electrons left in the n equals 2. N equals 2 is much closer to the nucleus. We still have a large charge pulling on them. And as we go from a neutral into a cation, our radius is going to go down. Now, if we consider instead our anions, from sulfur to sulfide, we are adding extra electrons. Our charge is still going to be the same. So in a sense, we're going to have more electrons for this charge to pull on, and our radius is going to go up. So if we compare a cation to the neutral, the cation is smaller. If we compare an anion to the neutral, the anion is always going to be larger than the neutral. All right, so let's do ionization energy. Ionization energy, we're going to shorthand this as an IE. And by the way, if your element has 10 electrons, it's going to have 10 ionization energy. But the first ionization energy is going to be the energy required to remove one electron. So if you take your element, so let's imagine our element is X. These are always done in the gas phase. And we put in our ionization energy, and we're going to put in our first ionization energy. We are going to make the cation plus an electron. Now, the tighter the electrons are held, the larger the ionization energy. The smaller the element, the largest ionization energy. And that is frequently the easiest way to look at it. So the easiest way to look at it is as the radius goes down, ionization energy goes up. So how does this look? Well, we know if our radius is going to increase down and then decrease across, it's going to be the largest here, which is going to be the smallest ionization energy, which is consistent with this data over here. And if we go over to here, these are going to be our smallest elements, and we are going to have the largest ionization energy. So again, as the radius goes down, the ionization energy goes up. So let's take a look, and we can do this entirely by size. We want to know which has the highest ionization energy, which simply asks the question of which is the smallest. So if we ask which is the smallest, we got to figure out where they are. So if we look at magnesium and we look at phosphorus, we know that as we go from the left to the right, it gets smaller. Therefore, phosphorus is going to be smaller than magnesium, and it's going to have a higher ionization energy. So the smallest radius, the highest ionization energy. Silver and copper. Well, copper is one row above silver, therefore copper is smaller, and it's going to have the highest ionization energy. What about calcium and rubidium? Well, calcium is here, and rubidium is here. Calcium is a row up, therefore calcium is smaller and has the higher ionization energy. What if we compare selenium and phosphorus? Again, one row up, phosphorus is going to have the highest ionization energy. All right, so let's look at successive ionization energies, i.e. not just the first electron, but more than one electron. And the key is to start looking at where the big jumps are, because where the big jumps are correspond to going in and removing electrons from the core. So if we look here, this value goes up by about 1500, this value goes up by another 1500, etc. But if we go from 418 to 3000, this goes up by almost 10. So that's our big jump. If we go to calcium, we go from 1100 to 5000, and then 5000 to 6000, so our big jump is right here. If we go to gallium, and yes, I'm going to skip one, our big jump is going to be right here. If we go from germanium, it is going to be here. So what does this correspond to? This corresponds to removing electrons from the core. So ionization energy 1 for potassium. Potassium is argon, 4s1. 4s1 is easy to remove, and that's that value there. And after we've removed it, we're going to have potassium plus, and it is going to be argon. Now, ionization energy 2 corresponds to taking an electron out from here. Well, if we take an electron out from the core, this is going to take a lot of energy, and we're going to have a big jump. If we go to calcium, calcium is going to be argon, 4s2, and pulling these two s electrons out is that ionization energy right here. When we get to this spot right here, we've pulled off 2 electrons and we have calcium 2 plus, argon, and getting that next electron off is that value right here. So what do we see? We see ionization energies increasing and increasing again, and then at some point they're going to go up a lot. When the ionization energies go up a lot, this tells us everything else past it is in the core. So the last thing we're going to look at, electron affinity is the energy that is released when an element in the gas phase gains an electron. Now this is not reverse of ionization energy. It's not, because if we take, for example, calcium, and we try to add electrons to it, it is not going to want electrons. Calcium is a metal, it wants to lose electrons. So this is not going to happen. What is going to happen, though, is chlorine is going to want to gain an electron. And when it does, it has a nice negative, meaning exothermic, meaning favorable electron affinity. Now, you think oxygen should want electrons as well, and that's true, but it wants 2, and this isn't quite as clean a trend as ionization energies or radius. But the basic trend in electron affinities are this, is that as the radius goes up, the electron affinity is going to go down, meaning the large elements, which are these guys down here, are going to tend to be metals. The small elements are going to be these guys right here, like fluorine. So fluorine, chlorine, bromine, iodine, these guys want to gain electrons. Now note the exception to this rule are the noble gases. Please note that noble gases are stable and they do not want to gain electrons. So as the radius goes up, ionization energy or electron affinity is going to go down, with the exception of noble gases, which do not want to gain electrons.